Good morning, everybody. Thank you for joining us in this education session here today. I'm sure you already heard an introduction of all the sessions that you will be able to listen to today. Unfortunately, I won't be able to be there in person this time around. I'm currently in Europe, and with travel being difficult with COVID testing and other associated issues, we decided it is the best to remain in place here. Hopefully, we will see each other pretty soon in one of the following events, as we're hoping to see the end of the tunnel here, of course. That being said, my name is Rolf Bienert. I'm the Executive Director of Lonmark International. And today I want to talk to you a little bit about buildings and the smart grid. Now, let me start here the slide presentation, but I will turn off my video for the presentation so you're not getting distracted here by looking at me. Okay, so let's first really set the stage and start talking a little bit about our understanding of what's really happening in the smart grid. After that, we'll review a few of the standards that you can see out there. This is, of course, only a small snippet. And then we will look at some regulations that are already out there. And hopefully the folks in the room will be able to also answer some questions for you if necessary here. So let's really now take a step back and think about what is happening here over the last few years. So when you think about, for instance, a telecom network, and when I started, for instance, at Deutsche Telekom in the 80s, really a standard telephone network or communication network in general looked just like this. You had a landline on one end, a landline on the other end, and in between you had a number of connectors, that would dial the numbers and connect you to the other party. And not even that long ago, in the mid-80s, in fact, around the time when I started at Deutsche Telekom in Germany, the fax machine came out. Before, of course, you had these funky things like telegraph and telegram and a few other mechanisms there. But really, the fax machine at that point was meant to be the killer app for telecom, which, of course, today we kind of smile about this, considering what we are seeing out there. At the same time, as I said before, the architecture here was really straightforward. And if a customer wanted even just a second landline, the customer service agent would look at him a little funny and wonder if they have a company or if there are many people living in a house and things like that. So you can imagine that when you're trying to look at today's telecom system and telecom networks, I wasn't even able to find a simplified picture of the entire system. So I think this was sort of the closest one of an end-to-end picture that I could see, but with interaction with the internet, IP systems, phones, from still regular kind of landlines, if you will, to others, you see that the network has just evolved so much over the last 40 years. And I'm kind of scared to say that number here because, like I said, I started at Deutsche Telekom in the 80s. It's unrecognizable. And now, if we fast forward from that first picture here in the 80s to what the utility grid looked like only a few years ago, and this is probably more about like 20 years ago in some areas, you saw a pretty straightforward connectivity here. You had some power plant, whether this was already something like a renewable energy in the sense, so generation due to hydropower and other things. Of course, not quite yet. A lot of solar and so on between 20 and 30 years ago. But any kind of power plant really fed into the transformer stages, which then transmitted the energy over the transmission lines, transformed down, of course, to a more digestible voltage, and then it ended at the customer. So very, very straightforward connection here. And while the markets between the production and your local distribution utility were always, a bit more complicated than most people understood, overall, the business structure was also very straightforward. The customer paid for a certain type of service, a certain level of energy that they could consume, and you would then simply read the meter, and you would be charged for that kind of money. Early on, even in the 80s and 90s, of course, you had different rates, for instance, during the night versus the day, and oftentimes the night rate was, of course, cheaper. And I vividly remember back in Germany in the 80s and 90s, these night storage heating systems were very, very common. So in the winter, you would have a system that either heats water or other materials during the night for a lower price energy. And then during the day, you would use that stored heat to heat your house, for instance, or other things. And you would use less energy during the day. So we're very, very innovative system at the time. Other systems, of course, heat pumps that would use the earth in your yard and so on as a source of heat were already coming out at that time. But nonetheless, everything was generation, transmission, and usage. There was really not much else. So now fast forward to the last, I would say, 10 years, maybe close to 10, 15 years, where some of these concepts came out. And all of a sudden, you're looking at this multi-layer graphic here. Some of you might have seen this before, right? Where we're looking at basically different layers of both communication as well as business, from the generation over the transmission, distribution networks. Now we're talking about distributed energy resources on the other end, and so on and so forth. And all these are connected, of course, at a field level, which still to some extent looks very similar to what you're seeing in this overall architecture from 20, 30 years ago. But now you're seeing much more interconnection here. You see these transmission stations, these substations talking to each other. You see different transmission systems talking to each other, and so on and so forth. And you just simply have quite a complex system out there. And we saw in the early 2000s, for instance, in California, where some of these market systems just simply broke down. And some of you might recall the Enron scandal at the time, where California had rolling blackouts because simply they didn't have enough energy because people oversold capacity. So it wasn't a technical problem that caused this shortage. It was rather a very hot, I believe, season. So a lot of energy usage, and this was meant to be compensated by some additional resources, some flexibility, demand response resources being sold into the market. But these resources were simply oversold. So they were sold to multiple people or multiple states. At least that's my recollection of all of this. I encourage you to read up on it. It's kind of fascinating. And California had all these blackouts going on, even in Silicon Valley. So that being said, you can already see why do we have this need of really integrating building automation systems from a commercial building perspective, an industrial building or facility perspective, as well as a residential building perspective. You can see everything is getting interconnected. Now, of course, some of you may say, well, yeah, this is all good and fine, but why would we care, or why would the customer care per se? After all, if we look at telecom, we see all these fancy things, right? We have everything from Facebook over other media communications that we use a lot, email, websites, everything in our daily lives, in particular in technology and the industry, runs over the internet. So it's just a must-have here. And again, speaking of all these social media applications, gaming applications, etc., these are also fun to use, right? So people want to have this. So they wouldn't want to live without their communication infrastructure, or maybe I should say most people. And the electricity grid, of course, again, you can argue it's not as cool, it's not as usable, it's not as touchable for the consumer. But if you really think about it, even when you talk to customers, you will notice that people want reliability. They want reliable power, right? They don't want outages, or want them resolved pretty quickly and things like that. So that's a big reason to contribute here. And of course, we would not do the right thing here if we wouldn't mention carbon emissions, whether this is due to regulations where you kind of have to be careful with your carbon emissions, but just simply also to really look at the climate, what's happening. And we see a number of states, countries, and areas where we're really seeing how energy distribution and transmission can first of all create problems, but also can become unreliable. Coming back to that first topic, when we have wildfires, flooding, and so on and so forth, which also ultimately leads to worse crops potentially and things like that. So there's a lot of aspects here to it, which I think the modern customer, for the most part, also understands. So yes, sure, smart grid, electricity grid is probably not as usable for the customer, if you will, as telecom applications, not as cool to use. But I think we will see a lot of our customers really being interested in using this wisely. I copied a link down here from Science Direct. It's a nice short read, an article about building automation and what to expect with the smart grid. So just let's look then at just a few examples of things that are already out there. This is by no means comprehensive. I just want to show you a couple of applications here that I just happen to have from Southern California, Edison, for instance. Charge stations, whether these are in industrial or office building environments, or of course also at residential settings, are becoming a big problem for utilities to manage. And Southern California Edison has already put programs in place, the Charge Ready program, for instance, how they can manage these charge stations by sending them price signals and different energy requirement signals, and so on and so forth. So you'll see more and more of that. And if you have a big facility, if you're working in a smart city implementation or a large campus, you will need to to take a good look at this, how you want to manage these fleets, how you want to manage chargers for employees potentially, and so on and so forth. Southern California Edison here chose to use a combination of two industry standards, OpenADR and OCPP, to control these charge stations, simply so that they can have a flexible supplier pool here of devices that use this. And I will talk a little bit more about OpenADR later on in the presentation here. So now shifting a bit to something much more simple, and again, I'm sticking to Southern California Edison. There's a lot of other examples out there as well. But another side of the business there is, of course, both residential and small medium business air conditioning systems. So they have, for instance, this bring your own thermostat model set up. So you can also find that on their website, where they're looking at controlling different size implementations. Oops, sorry, it looks like there's a little hiccup here in the graphic, but anyhow, they try to bring customers on board by offering them home automation, building automation, gateways, other incentives if they build automation into their commercial buildings. You can get certain incentives, be that paying the cost of the automation equipment, or of course also eventually giving the customers discounts and other incentives for their energy usage. So all of this really kind of filters back into maintaining the grid, maintaining the stability of the grid, integrating renewables that are much more fluctuating, of course, versus the good old power plants. And that's really also one of the critical points that I may have omitted here to some extent, but you saw it in your overview architecture. These distributed energy resources like solar on residential or commercial buildings, and then of course larger scale solar, wind, and so on, they will help to offset a lot of the carbon emission goals and things like that. But at the same time, they do represent issues here for the grid, as they are not as stable as traditional generation. So all of this together will require the smart grid to interact much more with the companies and everybody else involved here. So let's just look at a few standards, and I wanted to start with kind of an interesting standards framework here, which not too long ago came out from the IEC, and this was an interesting process. I put the link to the publication on the slide here. So in fact, Japan, together with some experts from Canada and Germany, started this effort here. And these are all industrial automation people that came together here. That's why I wanted to throw this in. It's probably not something that you typically look at, but if you are looking at building automation, control, process management to some extent, this might be an interesting framework to look at. So the IEC TS 62872-1 is looking at this interface between processes and controls in industrial facility and signals that you can get from the smart grid. So essentially what they did was they took demand response signals that come, let's say, from a utility control system, and tried to, I shouldn't say the decode really, but tried to understand them for their process management. So with other words, the simplest one would be, of course, if the price goes up. Let's say the price goes up at a certain time of the day, and the building or the manufacturing process or any other system there knows that they potentially can shift energy usage, right? They can, of course, save some energy, have some building automation, dimming lights where possible, changing air conditioning systems, heating systems, and so on and so forth. So the typical stuff that you are very familiar with. But of course, they also need to look at big machines, ovens, and other systems that may use a good amount of power to run, and potentially shift the usage here to cheaper periods and so on. On the other end of the scale, they were also looking at what does a lack of power, for instance, mean for us, or a change in power quality mean for us. So if you're just thinking about more sensitive manufacturing or semiconductor production and things like that, fluctuations in power or even power outages can potentially cost them a lot of money. So they were looking at all these considerations based on what they receive from the grid here as signals. So we're really an interesting framework if you are getting a little bit out of, let's say, just lighting controls and HVAC, but also look at some overall building automation here. But now let's get to some more, I would say, practical standards, for lack of a better term here. So one of the standards that's used a lot, and I'm sure you have probably heard the name by now, is OpenADR, and in particular OpenADR 2.0. And this is a communication protocol. So it's a web services protocol that runs between what's called a virtual top node, or a VTN. It's really a server. It's a server at the utility level, typically at the distribution utility level, which manages the resources, the areas, and so on. And from the top end, this server receives other grid information. So the utility knows, which areas are important to us, and where do we have shortages, or where do we have too much power due to solar and other things, and so on and so forth. So the utility basically processes all this information, as we have seen in this big architecture picture, and then decides where they need to send signals. And these signals can either be, for instance, price adjustment signals that go to these customer sites. They can be direct energy requests, use more energy, use less energy in a building. They can be capacity messages, like in particular for EV charging. As you saw on one of the previous slides, it's really important to be able to provide a charging network, a max capacity of what they can use or should use. But also, of course, and that's still a bit in the future, but we are seeing more and more interest in that, talking about energy bidding. So they could, for instance, offer you to buy some energy for cheap at a certain time. And if you are a campus, if you are a commercial building, if you're a hotel or something else, you could say, sure, I'll take it. I charge my batteries, I charge my electric cars, and so on and so forth. And then later on, when they say, okay, the price is going up, you can potentially feed back more of your energy, or reduce consumption if you have already pre-cooled or done anything else to compensate for this. So OpenADR works very much, or the main service in OpenADR, the event service, works very much like a calendar message, if you will. So you can receive a message that says, hey, starting today at 2, ending at 4, or it could say starting in 5 minutes, starting now. This is very flexible here on the time frame. The the end user can receive this message, this kind of calendar notice, if you will, and it can include a lot of different information elements. So like I said, it can include a price, it can include a request for your energy to go up or to go down, and so on and so forth. But one interesting factor in OpenADR is that it does not necessarily include any control messages. So this is totally up to your building automation system, and that's where now the interesting connection comes in, right? Whether you have, landmark in the building, or whether you have other technologies or a combination thereof in the building, doesn't really matter here, right? If you can receive an OpenADR signal in your control system via the internet, this is web services, you can really offer these buildings a great added value by processing these signals, and then you can use the building technology like landmark, for instance, to modify the devices on site and to change capacity and other things on that end. So really interesting, because it still leaves all the let's say the operational factor and the controls to you and to your innovative thinking on how you want to react to these grid signals. So again, what you should expect here is to get either dynamic price messages. We are expecting many utilities to go to more dynamic time of use prices, which obviously means that the price can change multiple times during the day, and you want to be ready to react to that. And it also could be that, as I mentioned, you get certain consumption related messages, either, hey, can you save some energy, can you save more energy, or we have a grid emergency, can you save as much as possible? Or buildings may have more specific contracts with a utility where you essentially put in control equipment which is sponsored or paid for by the utility company as an incentive, and because of that you have a specific value attached to that. So let's say you can save 50 kilowatts or something like that in your warehouse or in your conference center, and or in your food processing chain, in your restaurant chain, and so on and so forth. And these are the types of signals you can expect to receive here from the grid. Now, the next standard I want to talk about is kind of interesting. It's a little deeper in the building now, and that is a fairly new standard, even though the concept is already also 20 years old. Is the CTA 2045. This is a standard created by the Consumer Technology Association. There were a number of separate standards out there that did the same thing before, and some of you may have heard the name USNAP, which was a previous name for parts of this here. But in the last, I would say, 5 to 10 years, this was really commercialized to some extent, and there is now also a brand behind this, the EcoPort, which stands for like an appliance that has a tested and certified CTA solution built in. This is all brand new, so this is just coming online, and they're expecting certified devices in the next few weeks. In fact, I think just before AHR, they wanted to have some devices posted there. So there are some folks at AHR exhibiting already some of these tools here. So the CTA 2045 is a modular communications interface, and some people always I'm kind of hesitant, but I did write it here. Some people like to call it sort of the USB port for for appliances. I think it's more of a PCM CIA port for those of you that might recall these. So it's not quite as flexible as a USB port here, but as a matter of fact, it does provide a very simple, standardized interface, as you can see up in the top picture here on the right-hand side. This is the so-called AC version. This is the big unit here on the bottom right and on the top here, which uses AC voltage from the appliance. So we have, for instance, manufacturers like A.O. Smith and Skycentrix and others that build in these units here, and this port can be very much the same for any region you're selling your system in, and that's really the advantage here for you. If you are in the appliance space, you can add this port. You can say you're EcoPort ready or whatever, certified, and by just adding one of these modules here, as you're seeing in the pictures, you can add any type of communications to this appliance, and the regulations for this are already in place in Washington State. They require heat pump water heaters, for instance, to have the CTA 2045 port. I think Washington State and I think Oregon and California are also working on this, and this will really enable, as I said before, the appliance manufacturers to jump fairly easily on that bandwagon here and create something that they don't have to modify every other week for a different market here. So that's really the thinking behind this. The CTA 2045 has two form factors. You can see it here at the bottom right. So you have this AC form factor, top picture, as well as the real device bottom right here on the side. As I said, they receive AC voltage. And then there's a smaller unit. I should have probably shrunken this picture a little more. It's really pretty small, maybe 2 by 2 inches or so. This can slide into smaller devices, and this takes DC voltage from the units. So maybe more for instance, like thermostats or other products that are not as how should I say, big and bulky than like water heater and so on and so forth. Wanted to quickly look at the architecture though, because I want to make sure that this is understood here. So the CTA 2045 really only looks at the socket interface here. So it's basically these two green bars. So on the right side, you have the smart grid device, again, an appliance, a HVAC unit, a compressor, a thermostat, a fuel pump, for instance, could even be a solar system, etc., etc. And then you have this module, which is depicted here in the middle as the AC or the DC type module. And really, the interface is just this plug-in portion here. So we are using just the physical layer as the connection. We are doing a link layer handshake here. So on the physical layer, it's either an RS485 interface, that's the AC unit, or an SPI interface, which is the DC version. And then there's an application layer on top that does a few mechanisms. And for instance, you can imagine these as a just curtail now, or cycle down, cycle on, cycle off, and so on and so forth. So that way, you get just some basic information into this smart grid enabled device, and they would be always the same on this side. Then on the other side here, again, you have any communications in that module, and sometimes these modules will likely have something like a Wi-Fi node only that goes to a cloud-based controller. They could have this OpenADR spec built in. They could have other controls built in. And that's really the nice thing here. If you sell your appliance into a market that has different, or into different markets, I should say, that have different requirements, the utility might even provide this module for you, or you can package that module separately, sell it separately with the appliance here. So that's the idea behind this. So again, just starting up, but we'll see what we get here, hopefully soon. All right, last but not least, I want to briefly just mention this. There's a few slides here that you can look through on your own as well, but some of you may already know, of course, the California Title 24 building standards set here, in particular the energy code in part 6. So there's a few slides in here from Gabriel Taylor works at the California Energy Commission, and I just wanted to do this one slide here because I want to keep a little time here for everybody to switch to the next presentation. But non-residential buildings, which include again also the high-rise residentials, hotels, motels, will need to be able to process demand response signals. And these demand response signals, they should, in California, be communicated via OpenADR, the standard I mentioned earlier. So if you're really looking into the residential building market, the non-residential, so the commercial building market in California, you gotta keep that in mind and take a look at that. Again, there's a few more slides that look at the different areas here of this, but wanted to really give some more time also to some of the other folks here. And if there are any questions, since I can't be there, again, feel free to ask folks in the room. I'm sure there's a lot of knowledgeable people there, or just email me at rolf@longmark.org, and happy to have follow-up calls or answer questions via email on that. All right, with that, I want to thank you for just listening to me here today, and yeah, hopefully we'll see each other again pretty soon in the future. All right, have a great day and have a great show over there. Thank you very much.